In this video, we'll look at heavier radioactive isotopes and some applications of nuclear reactions. Some of you may have a radon detector at home. Radon is a heavier radioactive isotope, so is radon a big deal? So stop the video and think about these questions. Radon comes from uranium-238. The U-238 undergoes decay to several unstable isotopes till it finally gets to radon. Radon is an alpha emitter with a half-life of 3.8 days. Where do you live? This map tells you the uranium concentrations in your area and possibly how much radon is in your area. In California, radon zones have been mapped to predict the indoor radon level. So the issue is radon is a gas with a short half-life of 3.82 days. Radon is an alpha emitter, so if we inhale radon, those alpha particles can cause extensive damage to our tissues. There is a lot of uranium in our oceans, although at a very low concentration. We produced about 50,000 tons of uranium in 2011. What is uranium used for? U-235, another isotope of uranium, captures a neutron and then undergoes fission. That is, it breaks up into smaller atoms, produces more neutrons, gamma radiation, and a lot of energy. Stop the video and figure out how many neutrons are produced. And the answer is 3. All that energy released can be used to make electricity or a bomb. To make an atomic bomb, the U-235 has to be enriched from 0.7% to 90%. That's very hard to do. The first atomic bomb was equivalent to 20 kilotons of TNT. How much U-235 is equivalent to 20 kilotons of TNT? Stop the video and see if you can answer these questions. When U-235 undergoes fission, it captures a neutron and produces 3 more neutrons. Each neutron can react with another U-235 nucleus and produce 3 more neutrons, so that's a chain reaction. Critical mass is the smallest amount of U-235 or fissile material to sustain a nuclear chain reaction. To calculate the mass of U-235 that's equivalent to 20 kilotons of TNT, here's our problem-solving method. We know this is the amount of energy that's released when one U-235 nucleus undergoes induced fission. If we know how much energy is released when 20 kilotons of TNT explodes, we can calculate the number of U-235 nuclei, which is equivalent to that energy. Once we know the nuclei of U-235, we can work backwards to figure out the mass of U-235. 20 kilotons of TNT releases this amount of energy. That's from Hess's law. That's the amount of energy we need from the U-235 fission reaction. So if we divide this number by the energy from one U-235 fission reaction, we get the number of U-235 nuclei. Then we can use Avogadro's number to calculate the moles of U-235 nuclei. Then convert from moles to mass. So about 1 kilogram of U-235, which is smaller than a baseball, produces as much energy as 20 kilotons of TNT. The energy produced in a U-235 fission reaction can also be used to make electricity in a nuclear power plant. In a nuclear power plant, the uranium has to be enriched to 2 to 3%, and the nuclear chain reaction is controlled. So stop the video and answer these questions. So here are the answers. So in the reactor, the fuel rods consist of uranium. The control rods control the nuclear chain reaction by absorbing neutrons. The control rods, which can be made of boron, are inserted between the fuel rods. The moderator, which is water, moderates or reduces the speed of fast neutrons and turns them into thermal neutrons, which can sustain a nuclear chain reaction. And the coolant, which is also water, cools the reactor. So the fission reaction produces energy which heats up water. The water turns into steam. That steam then will spin turbines, which produces electricity. New materials are being developed to prevent corrosion and radiation damage in nuclear power plants. But really, would you want a nuclear power plant in your backyard? There's been 3 nuclear power plant accidents. You can compare the design of each nuclear power plant to answer this question. Our climate is changing, but we humans need a lot of energy. Burning fossil fuels produces carbon dioxide, which is a greenhouse gas. What about these other fuels? In 2013, we used about this amount of electricity. This is how it was produced, and this is how we used it. Most electricity was generated from fossil fuels. In 2003, most of our electricity came from burning coal, 20% came from nuclear. In 2016, most of our electricity came from natural gas. In the world, the main source of electricity is burning coal. Coal emits more CO2 than natural gas and oil, and also emits other pollutants. Scientists are trying to figure out ways to reduce the pollutants from burning coal. Coal waste in the form of coal ash has to be stored. That coal ash contains heavy metals which are very toxic. Nathan Lewis, a Caltech chemistry professor, calculated that more energy in the form of sunlight strikes Earth in 1 hour than all the energy consumed by humans in 1 year. Here are 3 solar energy projects that do not produce greenhouse gases. Gwyneth Cravens was skeptical of nuclear power, but she decided she would find out more about nuclear energy. Here's what she found. We get a lot of energy from a small amount of uranium. Nuclear power plants do not emit much radiation, so would you rather have a nuclear power plant in your backyard or live next to the U.S. Capitol building? There's more waste from batteries than all the retired nuclear fuel. And nuclear power plants are clean energy. Nuclear power in place of fossil fuels prevents many deaths from air pollution. One big issue with nuclear power is shutting down nuclear power plants. But is it possible to recycle nuclear waste? Newer generation nuclear power plants may be more efficient and reduce nuclear waste. This nuclear power plant uses sodium instead of water as the coolant. Perhaps a smaller modular nuclear power plant will be more acceptable to the public. It'll look like a Walmart. In nuclear fission, a big radioactive isotope breaks up into smaller ones. In nuclear fusion, the reverse happens. Here are the nuclear fusion reactions which occur in the sun. Note that hydrogen is the fuel, and the temperature in the sun is 15 million degrees Kelvin. Nucleosynthesis describes how bigger elements are made from smaller elements in fusion reactions. That's where we came from. So we come from stardust, but other processes are used to make even bigger elements. The nuclear fusion reaction in the sun is at 15 million degrees Kelvin, but if we do that on Earth, note that it takes a lot higher temperature. Another application of radioactive isotopes is in nuclear medicine. Note that different isotopes are used in either diagnosis or treatment.